Okay, so thank you for the the invite, and thank you for the attendees for hanging around the last hour and a half. So something a little bit different from what you've seen. So both myself and Susanna are in the chemistry department. I'm a lecturer in organic chemistry. And so what I want to talk about today is some of the work that is taking part in my lab, all around sustainable synthesis, and in particular, sustainable synthesis for medicine and future healthcare. So why should we be thinking about sustainability in terms of drug discovery and healthcare? So obviously, I'm not saying increasing life expectancy is a bad thing, of course, but this increase in life expectancy leads to an increase in the demand of what everyone would now agree is finite resources on the planet. And this then leads to huge challenges in terms of trying to identify new drugs or new sources of food or maybe even things like trying to grow more food in the same space of land. And effectively, we want to be able to do this and continue to have people live a healthy life without having a detrimental effect on the planet. So if we just have a look at this graph here, this is a graph that plots resources versus population, and then it compares per capita. And as you see on the graph in the kind of dark blue line, you can see the resources are we're around about here now in the graph, are now expected to take a pretty big plunge over the next 25 to 50 years. Whereas if we look at the pink graph, which is our pink line at the bottom, this is even more of a plunge, which is the resources per capita. So as the population increases, the amount of resources we can take is available for each person decreases quite dramatically. And so this has a huge kind of impact on industry and in general, just on everyday life. And one industry that this does take a massive impact on is in modern drug discovery. And so this issue isn't new. We have known about this now for the last 25 years. And big pharma have recognized this and put certain practices already into practice. And some of these have been readily adopted. And these practices all stem through these really important and now quite embedded principles of green chemistry. So green chemistry is essentially what it says on the tin, is how can we make chemistry a greener thing, or how can we make it more sustainable, environmentally friendly? And so these are the kind of the 12 things that green chemists have come up with to try and identify new ways to synthesize molecules or new ways to synthesize bulk molecules, depending on what you want to do. And in pharma at the minute, they're focused on three key areas. The first one is on the use of less hazardous chemical syntheses. So this is kind of self-explanatory. The less hazardous something is, the better it is for kind of everyone on the planet put together. The other one is design of safer solvents. So lots of chemical reactions don't take place in the solid state. They typically have to be dissolved in a solvent. Most of these solvents are quite environmentally unfriendly. So the industry itself has gone out of its way to try and identify more greener, sustainable solvents to do chemical reactions in. And the final one, which is the one that my group work in, is an area of catalysis. And this is basically the layperson ways of speeding a reaction up. So if a reaction can't take place in a kind of a useful or productive time frame, catalysis or catalysts derive from a range of different elements, which we'll talk about in the next slide, our next couple of slides, work to speed that reaction up to be a much more productive cycle. And so because this problem is not new, it has been worked on over the last 25 years, but the problem is kind of now becoming even more concerning, because modern drug discovery doesn't really look like drug discovery did 25 years ago. And so the fact that we're now designing much more complex molecules, because we have a better understanding of the underlying biology and biochemistry, means that these practices are typically now not enough to deliver these really important drugs for future healthcare. So if we just have a look at these three compounds here, these have been FDA approved and EMEA approved over the last maybe 18 to 24 months. And as you can see, the complex structures involved in both oncology, heart failure, and these multiple sclerosis drugs means that the chemistry that has to be developed to generate these molecules is typically quite complex and uses quite complex elements and elements that are quite scarce on the planet. So, for example, we don't really want to limit the amount of oncology drugs that potentially can save a person's lives. In terms of heart failure and multiple sclerosis, is hugely impactful on everyday life for millions of people across the world. So because drugs are becoming more complex, chemistry that has to be developed becomes more complex. And this is where my lab comes in. And we start to develop new chemical reactions to try and identify new ways to put molecules together. And if you, apologies for anyone who's colorblind, but if you look at the molecules in blue, you can see that all of these have the same type of elements. So they've got nitrogen, carbon, elements, and particularly they have substitution that is effectively right next to the nitrogen atom here. So this is what my group pretty much are concentrating on over the last 18 to 24 months. So we have a look at this periodic table of elements. So I'm sure some people this strikes a lot of fear, but for a chemist, this is our first love, and I think it will always be our first love. So if we have a look at the periodic table here, most of the new chemistry that's developed to access these important and complex scaffolds typically uses these 8 elements here at the bottom. And as I'll talk through in the next slide, this isn't necessarily a good thing. What my lab tried to do is we tried to move away from these 8 elements, and specifically we try to concentrate on the left-hand side of the periodic table, and I'll explain why in a second, as well as on the right-hand side of the periodic table. So we're very left-wing or right-wing in our chemistry. And the reason we want to do this is not very clear by looking at the periodic table, but if we have a look at a different version of the periodic table, which focuses on natural abundance of elements, we can see pretty clearly why this is a problem and why it needs to be fixed pretty rapidly. So if we have a look at where the compounds or where the elements that make up a lot of our new complex catalysts, they exist in this kind of range down here, where they're either have a rising threat from increased use, or they've effectively got a serious threat to their natural abundance over the next 100 years. And so, of course, the more that we need to use these, and the more that we need to make more molecules and more agrochemicals, these will decrease exponentially. Whereas what we do in my lab, we try and focus on just the green elements, both in color and in the sustainability terms. And specifically, we look at calcium, which is highly abundant. It's the 6th most abundant metal in the Earth's crust. So we know that we can access this quite readily from lots of non-precious kind of ecosystems. And the other one we look at is using silicon. So silicon is everywhere. I mean, it's in sand, so it's pretty ubiquitous across the planet, and we can access lots of unusual reactivity and lots of unusual chemistry by just thinking a little bit more deeply about using these type of compounds and elements. So what I want to do is try to use these more abundant elements in chemical synthesis, and this is only one solution of hundreds of different solutions that very smart chemists, much smarter than I am, have come up with to try and identify kind of ways and means we can use new chemistry to make sustainable drugs, or make drugs more sustainable in the future. The problem is, and from an academic point of view, it's not really a problem, but the chemistry of this is hugely underdeveloped. Over the last 5 to 10 years, the use of calcium has kind of taken off a little bit, but again, we're pretty much the only people in the UK that we know of that are using this as a catalyst in chemical synthesis. Because this chemistry is undeveloped, we need to actually focus in the lab and try to develop some new chemistry. And this is where these very happy, shiny looking people come in. So this is my research group. As you can see there, I have let them out of the lab to get some sunlight, so they all look very happy. This is them in their natural habitat on the right-hand side, working very diligently away in the lab. So this is the people who actually do the research. I don't do any research in the lab at all. So I think that my group would not enjoy that too much. So these are the guys who actually do this every day for their PhDs and their master's projects. So as I said, the solution then is to use more naturally abundant elements. And as I said, we use calcium as a new and sustainable catalyst. So we do this because calcium, as I mentioned before, is highly naturally abundant. It's pretty easy to get from the ground. And therefore, because its availability is so wide, the supply issue is effectively a non-issue. We can get it from pretty much everywhere across the globe. It's non-toxic, which is really useful in terms of designing new processes and scaling processes up to make tons and tons of molecules and tons of these drugs. If it's non-toxic to start off with, we don't have to worry about containment, for example. Its chemistry is highly versatile. So from an academic or from a chemist point of view, this is really useful. I'll not spend too much time on this, but this is just to show that through kind of careful control of our reactivity and careful control of what the calcium catalyst we use, we can tailor its reactivity to be whatever we want it to be, essentially. And it does take a little bit of deep thought, but that's the whole point of what we do in my lab. And we think when we design projects and design new ways to make compounds, we embed this idea of sustainability through design. So basically, we want, if we do a chemical reaction, the byproducts that those chemical reactions produce are typically quite toxic. So we want to minimize these byproducts in the reactions that we develop, or if the byproducts have to be produced, they are either non-toxic or environmentally benign. We also really deeply think about the idea of atom economy. So that means that whatever goes into the flask, so we have a reaction flask, whatever goes into that flask should really come out again as a productive thing. So everything we put in as a reagent comes out as our final product. We typically try to use less harmful solvent if at all possible. Sometimes this just doesn't work in practice, but we do try and aim for the use of these less harmful solvents, both in terms of human health, but also in terms of environmental impact. We also want to design reactions that are quite quick, so they're less energy intensive, so we don't have to heat things up for too long, cool things down for too long. We can kind of try and speed these things up to such an extent that you can wait 15 minutes and you get your product in your hand. And also we want them to be productive. So this might seem a bit obvious, but by productive, we mean high yielding. So we want everything we put into the flask should come out, but they should come out as 100% or close to 100% of what we've put into that flask. And so this is a type of scaffolds that my lab makes. We make these because they're impactful for medicinal chemistry and for drug discovery. And so over the next couple of slides, I just want to introduce some of the medicinal chemistry or drug discovery programs that we're currently working on in my lab, and to show you how our chemistry impacts how we discover or how we design new drugs. So the first project that we're working on is an MRSA drug discovery program. So MRSA is known as the hospital superbug. It's effectively, MRSA stands for methicillin-resistant Staphylococcus aureus, but actually we think about it now as a multi-drug resistant Staphylococcus aureus infection. If you have the unfortunate event that you get MRSA, you effectively get treated by vancomycin, which has a huge amount of side effects. And you have to stay in hospital for a prolonged period of time with lots of kind of medical screening to make sure your liver and kidneys are acting as they should. So my lab are trying to do is identify molecules that are less toxic to humans, but much more toxic to bacterial cells. And so one of the scaffolds we're working on is this compound here. So this is an analog of penicillin, or the analog of the core of penicillin. And if we look in the literature, which is what we typically do as an academic, we see that trying to access these type of compounds is really easy. There's lots and lots of chemistry developed to make these type of molecules. But if we want to increase the complexity, so if we want to add an extra yellow dot in this case, the chemistry for this is pretty much not being described anywhere in the literature in any great detail, which means it's an opportunity for us to develop some chemistry, but it's not very good if we want to design some drugs. So what a very talented PhD student, Ashley, in my group, has done over the last couple of years of his PhD, has developed a huge range of these type of reactions, or these type of compounds using a single type of reaction. So I'm not going into too much detail, but what we do here is we dehydrate. So that means we just lose water from the molecule to form this intermediate here, which is very, very reactive. Because it's very reactive, we can react it with lots of things that are inherently unreactive. In this case, it's just a second yellow dot. which we produce our scaffolds in very high yield. We typically produce them after about 15 to 20 minutes. And as you see, everything that goes into this reaction is effectively in the product, except for, and this is really important, except for water here, which we see on the right-hand side. So the byproduct of this reaction is water, and hopefully everyone can attest to the fact that water is very non-toxic unless you have too much of it and you're in it for too long. The second project that we're currently focused on is on a cardiovascular disease project. And we're really interested, so myself and collaborators in Manchester are really interested in understanding and eventually inhibiting how clots form within the body. So that's not only just in terms of what the kind of the causative effects are. So we all know high cholesterol, for example, is a causative effect, but what's the biochemical pathway from having no clot to having a very dangerous clot that can cause brain hemorrhages or whatever else type of disease. And in terms of what we're looking at this compound here, ditazole, which inhibits something called platelet aggregation. So platelets are in your blood, they aggregate, they form. That's the kind of the initial clot formation event. Problem with ditazole is quite toxic. You can't really give it to lots of people with underlying health conditions, which are typically those who already have cardiovascular disease. So what we want to do with our collaborators is identify a new, safer version of ditazole to treat these type of clot formations, or to prevent clot formations in the first place. So if we look at the core of ditazole, we have this heterocycle shown on the right hand side of the screen, and basically all you just have to concentrate on is the fact that we want to change what decorates this internal core. Again, you're looking in the literature, there's not many ways to modulate these type of reactions. There's no way, or there hasn't been very many ways until we published our results again with Ashley, to modularly change what you have on the core here. So what Ashley did over the course of a few years again was develop another kind of type of dehydration reaction, again forming a type of reactive intermediate here, which again is effectively just very, very reactive. Treating these with a molecule which has got this red spot that you see on the core here, to give these molecules shown here, which is exactly what the target molecule was that we wanted to identify. Again, the byproduct of this is methanol, which is slightly more toxic than water, but it's very easy to get rid of and is not overly toxic in terms of environmental impact. A final project is in the area of childhood epilepsy. So with colleagues at Newcastle University, with structural biologists and biochemists there, we're synthesizing molecules to treat a rare form of childhood epilepsy. So this epilepsy is not neuronal, which is typically what you see in epilepsy. It's actually metabolic in its pathology. So these kids who present with this type of epilepsy can't be treated with normal epileptic drugs. It has no effect. And so what we have done is we've identified this type of scaffold. Again, you can see with these simplified dots, we want to start to change what's on this molecule to make a more efficacious drug. Again, these are incredibly difficult to make. And if you, again, go into literature, there's not many ways to do this. There's a few, but they're not very kind of environmentally friendly. They don't scale up very particularly well, or they use quite intense and quite costly type of equipment. So what we have done again is identified a new way to make these, again using the same type of chemistry I've just shown, via this type of dehydration, once again forming this very reactive intermediate that's shown here in the blue square, reacting it then with a red dot to give, not only can we give these two positions substituted here, we can also substitute at this position here. So this gives us a huge range of potential molecules that we can go off then and screen against the biological target that we know is causing this form of epilepsy. And hopefully then, not only do we find a starting point for drug discovery, but we also do something called de-risking the target, which I'll talk about in a slide's time. So what is the actual impact of what work, or what is the impact of greening up sustainability in drug discovery, and what's the impact of the work that my lab is currently doing? So first things first is we try and improve something called the screening library. So when drug companies go off to develop a new drug, the first thing they do is screen a huge numbers, we're talking hundreds of thousands to millions of small molecules, to identify a hit, or to identify a molecule that seems to bind to the biological target that you want to inhibit. So by increasing the complexity of these screening libraries and increasing the fact that we can change pretty much every position on those screening libraries, will improve those libraries to go off to make better drugs. We also reduce toxic byproducts. So some of the projects I've already discussed, we produce very innocuous byproducts such as water, methanol, ethanol, or we produce these type of silicon compounds down here, which are, again, they're used in the lubricant industry, so they are very innocuous. And the final thing that we try and do, the final target or impact of our research, is in this area called de-risking biological targets. So drug companies will inevitably always want to find a drug, but it is effectively a business at the end of the day. And they're typically risk averse, most businesses are. So what academics are poised to do are to do something called de-risking, or validation of biological targets. So if we can show the biological target has a role in a disease, and we can make a molecule that will never be a drug, but is a good starting point for drug discovery, and we can show that molecule has a beneficial effect on the disease that we want to treat, that gives the pharma companies lots of confidence then to go off and spend their huge amounts of money to develop these drugs and go into the clinical trials that you heard about before. But before all of that happens, an academic like myself, or our colleagues around the world, try and de-risk these targets to show that they have not only an important effect in biology, but we can also ameliorate the effects of the disease. And so where do we see this going over the next 5 to 10 years? So my lab, as I said, are very focused on using calcium and silicon. But if you look at this periodic table, or this type of periodic table, there's lots of other green that could really be used here. And so what we're now currently focusing on, or what I'm currently focusing the kind of future PhDs in my group, is in using sodium and potassium, again, a very well-known, very easily accessible element in catalysis, as well as using aluminium in catalysis. As you can see, all three of these are pretty highly sustainable. They're useful in lots of different chemistries, but we just need to think a little bit more deeply about how we can use this chemistry to synthesize and develop molecules that have an impact, or molecules that have a purpose, which is what my kind of ethos in the group is all about. As I said, this doesn't happen by me. I don't do very much in the lab anymore. So it's all down to these very talented and incredibly hardworking individuals shown here. This is a group picture a few years ago. As you can see, they are allowed out of the lab at some stage. And this is us just discussing some chemistry here. Of course, this also doesn't come without a considerable amount of funding. And I just want to thank a lot of these funders for having the faith in what we're doing and trying to move drug discovery into the kind of 21st and 22nd century, I guess. Thank you very much.